Okay, our second talk of the day is by Richard Nally, and Richard's going to tell us about supersymmetric flux vacua and Calabi-Yau modularity. Take it away, Richard.
Okay, so first of all, thank you to the organizers for the invitation to speak. I appreciate it. So I'm going to be telling you about some recent work with Shamit Kachru and Wenjia Yang. And here are Shamit and Wenjia. So before I start, I just want to give you a little overview of what we're going to talk about today. So in string theory, we usually take 6 of our dimensions to be a Calabi-Yau threefold. So we get a 4D theory. And usually we think about the complex geometry of our compactification spaces. And this has taught us a lot about string compactifications and how they work. String duality, strongly coupled field theories, mirror symmetry, all that good stuff came out of viewing these guys as objects in complex geometry. You think about period considerations and things like this. On the other hand, the same objects, many of them appear in the study of arithmetic geometry, which is the study of varieties defined over the rational numbers, which is the setting for the Langland's conjecture and the proof of Fermat's last theorem, and a lot of very good 20th century mathematics. So a natural question to my mind and the mind of my collaborators is, does this arithmetic point of view ever have anything to do with string theory? So in this talk, I'm going to tell you that yes, supersymmetric flux compactifications have a arithmetic structure that's quite interesting. And I think this is a interesting link between physics and a fairly exciting area of modern math. And just to kick off, I can link you to some related work. Moore studied the relationship between string compactifications and arithmetic. And then recently, this has been kicked off again by Candelas and some papers by Wenjia Yang. So I want to start by reviewing the basic physical setting for this work, which is supersymmetric flux compactifications. So we start off with 2B string theory in 10 dimensions, compactified to 4 dimensions on a threefold X with a H2 one-dimensional complex structure moduli space M. And at each point in complex structure, we have a way of breaking down the middle cohomology, H3 of X, into a Hodge decomposition where I have 3 0 forms, 2 1 forms, and so on and so forth. And so 2B string theory has 2 form gauge fields, which have 3 form field strengths, F and H. And it also has an axiodilaton tau, which lives in H mod SL2Z. So from F, H, and tau, we define a complexified flux G3 as F minus tau H. And so in flux compactifications, we take F and H to have integral fluxes through our threefold. And when we do this, our dynamics are governed by a superpotential. W is the integral of G3 wedge omega. And to find flux vacua, we extremize W with respect to the complex structure moduli as well as the axiodilaton. So we set the covariant derivatives of W equal to 0 and solve. And you can show that we have a flux vacuum for fluxes FH and dilaton tau at a point X star in complex structure moduli space if G3 is in H21 of X star plus H03 of X star. And so when W equals 0, we say supersymmetry is preserved. So we call these supersymmetric flux vacua. And because W is the integral of G3 wedge omega, to have a supersymmetric flux compactification, we need G3 to just be an H21 of our point in moduli space. And the reason why is if G3 had a 0,3 component, then G3 wedge omega would be non-vanishing. and so G3 and H21 plus the constraint d tau W equals 0 lets you show that F and H themselves have restricted Hodge type. They have to be in 2,1 plus 1,2 with no 3,0 or 0,3 components. And so I want to emphasize that this is very rare. It's in some sense a non-generic phenomenon because you need to solve an over-constrained system of equations to make this happen. But nevertheless, they do happen, and they can happen either at isolated points in moduli space, or they can have continuous loci of moduli space, where for a range of complex structure parameters, you can actually have supersymmetric flux compactifications. And so at this level, this is fairly analogous to the attractor equation. In the attractor equation, you have an integral charge in 3, 0 plus 0, 3. And here we have f and h in 2, 1 plus 1, 2. So they're formally somewhat analogous. And given that some attractors, rank 2 attractors, are arithmetic, we can ask whether supersymmetric flux compactifications have any arithmetic to them. And I will tell you that the answer is yes, but first I'm going to introduce some arithmetic geometry. So far, everything I've said has been rooted in complex geometry. I've been talking about periods and the integrals of things by omega, and that's the field of complex geometry. But these same objects, many of them can be studied in arithmetic geometry, where instead of thinking about complex manifolds, we think about varieties defined over the rationals. And varieties are just a fancy word for the graphs of polynomials. So in the simplest example, some tori can be viewed instead of objects in complex geometry, instead of donuts, they can be viewed as elliptic curves over Q. So they turn into a graph like this instead of a donut. And so all that happens when you view something as defined over Q is you take its defining equation and you restrict all of the variables in that defining equation to only ever take values in the rational. So for an elliptic curve in P123, we can write it in Weierstrass form. Y squared is equal to x cubed plus ax plus b. And if we're viewing it over Q, we take a and b to be integers, and we restrict x and y to only take rational values. And from this Weierstrass form, you can write down two invariants, the discriminant delta and the J invariant. And we have a smooth curve unless delta equals 0. So I've told you what an elliptic curve over Q is. Now I should tell you what you do with it. So if I give you an elliptic curve like this defined over the rationals, so where a and b are integers and x and y are rational numbers, you can reduce it over finite fields fp. And to do that, you literally just take these integers a and b and you replace them with their reduction mod p. And then you let x and y only take values in fp. So, 0, 1, 2, 3, dot, 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 p minus 1. And then you check what points satisfy this equation mod p. And so as long as my prime p, the p with respect to which I'm reducing, doesn't divide delta, the curve will be non-singular. And we call a prime p good if delta is non-zero mod p and bad if it is 0. And so once we've reduced over fp, we can ask how many points there are on the elliptic curve. X and Y can each only take a finite number of values. So there is a finite number of total points that can possibly be on the elliptic curve. So in general, elliptic curves over Q can have infinitely many points, but over FP, they can only have finitely many. So you can roughly ask how many points you expect there to be. And those are the p values of x I can plug in. For each value of x, you sort of expect on average, there can be one value of y satisfying the equation. And then there's another point, the point at infinity, which comes from the fact that we're really working in projective space. So there don't in general have to actually be p plus 1 points on the curve. There can be some x for which there aren't a y, or some x's for which there are two y's that satisfy the equation. So we can define a scatter coefficient, AP, which is the expected number of points minus the actual number of points on the curve over FP. And these point count coefficients, AP, those are the basic objects of study in arithmetic geometry. And the point of these APs is the modularity theorem of Wiles and others, which says that for every elliptic curve E defined over the rationals, there is a modular form such that whose Fourier coefficients reproduce the point count coefficients of my elliptic curve for all good primes P. So the slogan to keep in mind is point counts give the Fourier coefficients of modular forms, or more generally, some automorphic object. But for elliptic curves over Q, there's a very precise statement, which is that the modular form is in fact a weight 2 cusp form for some gamma naught of n, where n is determined by the bad primes of the elliptic curve. So this is not something that physicists do very often. So I want to quickly go through an example of doing such a reduction. So let's start off with the elliptic curve y squared is equal to x cubed minus 4x. So you can compute its J invariant and discriminant. J is 1728 and delta is 4096. 4096 is a power of 2, so the only bad prime is 2. So we can reduce mod any prime other than 2 and get a smooth object. So for instance, if I reduce over F3, I'll get the elliptic curve y squared is equal to x cubed plus 2x. And so if x and y can only be valued at 0, 1, and 2, there are 3 points that satisfy the equation, 0, 0, 1, 0, and 2, 0, plus the point at infinity. So we have 4 points. And so A3 is 3 plus 1 minus 4, which is 0. On the other hand, we can reduce over F5 to get the elliptic curve y squared is equal to x cubed plus x. And there are again 4 points, 0, 0, 2, 0, 3, 0, and the point at infinity. So we have 4 points, and A5 is 6 plus 1 minus 4, which is not 2. It's supposed to be 2. So if you have a weight 2 eigenform, there is a particular modular form, which is q plus 2q to the 5th minus 3q to the 9th, and so on. And it has b0, b3 equals 0, b2 equals 5, which match the point counts we just did. So you can check that this pattern continues. That is, for every prime p, there is this modular form, the Fourier coefficient AP matches the point count coefficient you get from the elliptic curve. And so that's how we compute rational models. They go on in this way. And we've skipped an important step so far, which is the choice of a rational model. So over C, which is how we're used to thinking, tori are entirely classified by their J invariants. If there's only one torus with fixed J and which is the same as fixed tau. There is a torus with tau equals I. But over Q, there are infinitely many arithmetically inequivalent elliptic curves with the same J. And the easiest way to see why this is true is to look at an example. So think about the two elliptic curves y squared is equal to x cubed minus 4 and y squared is equal to x cubed plus 4. So these both have J equals 0. So is complex tori, they're isomorphic. But the map between them you can check is generated by the coordinate redefinition y goes to iy. And so this has an I in it, so it's not a Q isomorphism. All Q isomorphisms are of the form y goes to like cy for some c and q, but since I is not a rational number, this isn't a Q isomorphism. So when we have two elliptic curves like this that have the same J invariant, but are not isomorphic over Q, we say they're different rational models for the same torus. And just to very explicitly see why these aren't the same, you can reduce them over F7 to show that to get y squared is equal to x cubed plus 3 and y squared is equal to x cubed plus 4. And so these just have different number of points on them. And so since the point counts determine the modular form, these two elliptic curves are associated to different choices of modular form. So that means the arithmetic of these two elliptic curves is different. They're not equivalent arithmetically. But in string theory, we would never view them as different. In string theory, we usually work up to C isomorphism classes of Calabi-Yau threefolds. And so this is different than how we usually think about it. And I emphasize this point now because it will be relevant later. But the takeaway is if I give you a variety over Q and tell you what its modular form is, I've picked a particular rational model for it. I've not just picked a point in complex structure moduli space, I've also picked some additional data. And so far I've been rather concrete, and this is a choice. It's a concrete point of view on a rather more abstract story. So instead of an elliptic curve, let's say I give you a n complex dimensional variety over Q, so 2n real dimensional. Its middle cohomology, Bn, furnishes Hn furnishes a Bn dimensional representation of a group called the Galois group of Q, which is the group of automorphisms of the algebraic closure of Q that fix Q pointwise. So this means the details of this group aren't particularly important to the talk, but the idea is that I take Q, I adjoin to it the roots of all polynomials, and I look for automorphisms of the enlarged group that fix Q pointwise. So for instance, there's an element of Q bar which is Q bar contains Q adjoin I, and Q adjoin I has an automorphism complex conjugation, which moves everything with an I around, but leaves Q fixed. And so that's in the Galois group. And so the details of this group don't really matter. What matters more is the fact that I have a Bn dimensional representation. And so for an elliptic curve E, B1 is 2. So we have a 2D rep rho 2. Similarly, from a cusp form F, you can create a 2D Galois rep, rho 2 of F, and you can state the modularity theorem as for every elliptic curve E, there exists an F such that rho 2 of E is equal to rho 2 of F. The statement of equality of point counts is exactly the same as the statement of equivalence of Galois representations. And so this more abstract point of view is how mathematicians in the field will talk about this. And this is actually how we're going to be able to apply it to string theory. So to apply it to string theory, I should tell you something about the modularity of Calabi-Yau threefolds. Tori are, of course, Calabi-Yau onefolds, so it's natural to ask whether we can generalize this to higher dimensional Calabi-Yaus. And modularity of threefolds over Q is still an active area of research. It's, people are still writing papers on it, even in math, and it's very much in the phase of experimental mathematics. There aren't that many uniform results, but there are a lot of examples. So if I should tell you something about the modularity of threefolds over Q, I should tell you what a threefold over Q is. And so the examples in this talk are going to be of the form of projective hypersurface, where I pick all of my coefficients to be rational. So there is a Calabi-Yau threefold in weighted projective space 1, 1, 2, 2, 2. It's defined as the zero locus of this polynomial. And if I pick my coefficients psi and phi to be rational, this descends to a polynomial over Q just by restricting all my x's to be rational numbers. And so if psi and phi are rational, I can do point counts on this variety, and I can ask for modularity. But modularity for threefolds is technically a much harder problem than modularity of elliptic curves. And there are a few reasons why. One sort of kind of boring reason is that numerically, even computing the point count coefficients is computationally hard. But sort of the deeper reason why is that the Galois rep associated to a threefold over Q is B3 dimensional. And so in general, B3 can be very large. But we understand Galois reps very well if they're two-dimensional, and rather less well if their dimension is bigger than 2. So if I hand you some B3 dimensional Galois rep, it's in general very difficult to say anything. But sometimes this Galois rep is really two-dimensional. If H21 is 0, i.e. I have a rigid threefold over Q, rho 2 is two-dimensional, and all of the same tools we developed to study elliptic curves can be brought to bear to study the modularity of rigid threefolds. And indeed, for rigid threefolds, there's a uniform theorem. Every rigid threefold over Q is associated to a weight 4 cusp form. Now there is another way to get a 2D Galois rep out of a threefold with H21 not equal to 0. This big Galois rep can become reducible. And in particular, if it decomposes into the sum of a two-dimensional piece and a 2H21 dimensional piece, we can focus our attention on the two-dimensional piece and study it directly. And sometimes rho 2 can be related to the representation associated to an elliptic curve. And when that happens, buried inside the point counts of my Calabi-Yau threefold are the Fourier coefficients of a weight 2 cusp form. And so subject to some technical assumptions, this happens when there is a 2D subspace of H3XQ, where everything in my 2D subspace has Hodge type 2, 1 plus 1, 2. But that always happens in supersymmetric flux vacua. The definition of a supersymmetric flux vacuum implies that our fluxes, F and H, are in H21 plus 1, 2. So we take their Q span, and we have a subspace, H flux, inside H3 of XQ, such that everything in this subspace has Hodge type 2, 1 plus 1, 2. So the previous result kicks in, and we have our main result, which is that supersymmetric flux compactifications over Q are, up to some technical assumptions, modular. And they're modular in such a way that they're associated to weight 2 cusp forms. And I should say that you can apply a similar argument to rank 2 attractors to see that they are associated to weight 4 cusp forms. So since there are some pretty powerful conjectures in play here, we should try checking this in examples. And so the best sort of examples to check this on are the examples where we have continuous families of flux compactifications. And so such an example is given by the Calabi-Yau threefold I gave you earlier. It's the Calabi-Yau threefold in P11222. So this is its defining polynomial. And as long as psi equals 0, it was shown by de Wolf that we have a supersymmetric flux compactification for all phi. So at psi equals 0 and then all rational phi, I have a supersymmetric flux compactification over Q, and we expect them to be modular. And in particular, we sort of think that there should be a different modular form for each gamma naught of n. So inside the moduli space of this threefold, we literally have an infinite number of points we can check. And so the hard part is doing the point counts, but fortunately in this example, the point counts were already done by a mathematician. So we can use the known point counts and look for the Fourier coefficients of weight 2 modular forms. And so you can do that, and it works. So in this table, I've given you some explicit values of phi, as well as modular forms, which are labeled by their n, the level in gamma naught of n. And so in this table, I've given you, a few values of phi, and you can really just look at the point counts for each of these phi and see that there is a modular form buried in them. So given that flux modularity is really a conjecture, I think this is pretty strong evidence for the conjecture. And so there's an obvious question, which is, do these modular forms mean anything physically? So unfortunately, we still don't know what the point counts are supposed to mean physically, but we've found the weight 2 eigenforms associated to elliptic curves. And so since elliptic curves are pretty natural in string theory, one might hope to find the elliptic curve somewhere in the flux compactification. And so to define a supersymmetric flux compactification, we don't just need fluxes, we also need a dilaton tau. And so you can think about this tau as the tau of some torus. This is where F theory comes from. And indeed, the dilaton of the flux compactification is the tau of the elliptic curve associated to the modular form associated to the threefold. So that's a mouthful, but I pick a point in complex structure moduli space, admitting a supersymmetric flux compactification with some tau. If it's the flux compactification is defined over Q, it's associated to a weight 2 eigenform. Weight 2 eigenforms come from elliptic curves. Elliptic curves have a tau, and that tau is the same as the dilaton. And so this was checked for one example by Candelas, and then we checked it for infinitely many more examples. So in our favorite example, the Calabi-Yau threefold in P11222, you can compute J of tau as a function of phi. For each phi, we get a different choice of dilaton, and you can compute J of this dilaton, and it's some rational function in phi. And so what this means is that for every rational phi, we get a rational value of J, and there is an elliptic curve associated to that J. Now we can be very explicit. F theory, so a orientifold of 2b on a threefold is dual to F theory, and F theory on an elliptically fibered fourfold. And Sen gives a very explicit construction of the Weierstrass form corresponding to any fixed choice of tau. So from Sen's construction, you can specialize to a supersymmetric flux compactification, and the Weierstrass form you get is of this form: y squared is equal to x cubed plus c minus 3, x plus c minus 2. And so now for this elliptic curve, J is completely unfixed. And the reason why is because J is determined by C, and C is an arbitrary parameter. We can fix C by demanding that this elliptic curve has the right J invariant, that J of C is equal to J of phi. And so for our example, for 11222, you can just solve this equation to find C as a function of phi. So we get C of phi is equal to 9 over 4 phi squared. So you plug that in and you have a one parameter family of elliptic curves. And for each rational phi, we get an elliptic curve defined over Q with the right J invariant to produce the modular form over associated to the threefold. And so I only showed it for P11222, but you can check this for several other examples. So this is good, but it's not great. And the reason why it's good but not great is that we haven't picked a rational model anywhere. Sorry, we have picked a rational model and it isn't the right one. For any fixed value of phi, you can compute the modular form associated to this elliptic curve and ask what it is. And for general phi, the elliptic curve associated to this family of the modular form associated to this family of elliptic curves is simply not the same as the modular form associated to the threefold. So can we do any better? And I just want to emphasize that you might not be able to expect that we should do any better. F-theory doesn't know about rational models. It doesn't know about rational structures. So asking F-theory to give you a choice of rational structure might sound a little optimistic. But indeed, it can give it to you. And so as a hint, you can look at what happens as phi goes to 0. And as phi goes to 0, this Weierstrass model becomes badly behaved. But that's a coordinate singularity. There's nothing actually singular in the threefold or the fourfold at this point. So you can look for new coordinates that resolve this singularity. And so if we redefine y goes to root ay, we get a new Weierstrass model with this undetermined coefficient a in it. Now we can cheat by plugging in the rational model associated to phi equals 0. So phi equals 0 corresponds to the eigenform for gamma naught of 64, which is associated to the elliptic curve y squared is equal to x cubed plus x. So we can get out this rational model at phi equals 0 if we can pick an a as a function of phi, such that this Weierstrass model has the right limiting behavior as phi goes to 0. And so you can just sort of stare at these limits and see that that a choice that works is a of phi is equal to 2 phi over 3. And so if you plug in this choice of a of phi to this Weierstrass model, you get a new one parameter family of elliptic curves. It's defined over Q for all rational phi, and moreover, for all rational phi, it has the same J invariant as the modular form associated to the threefold, and it has the right limit, and the limit as phi goes to 0, it reproduces the modular form associated to the threefold. But it's actually even better. By fixing this choice of rational model at phi equals 0, we get a rational model for all other rational phi, and for all phi, you can check the modular form associated to this elliptic curve is the same as the modular form associated to the threefold. So we checked several million examples, and for all the millions of rational phis we checked, the modular form associated to this elliptic curve is the same as the modular form associated to the threefold. So subject to one choice of rational model, this F-theory construction is giving us an infinite number of other rational models. So I'd like to reiterate that there's a sense in which this is very surprising. F-theory doesn't know anything about rational models, and since paper, nothing special happens for rational J, but indeed, F-theory knows enough about rationality that it can give you an infinite number of rational models by hand. So that's what I wanted to say. Let me just conclude quickly. So in string theory, we usually talk about complex geometry, but the same objects appear in arithmetic geometry, and it's interesting to know if this arithmetic geometry is ever related to physics. And so in this talk, we've argued that it is, and that supersymmetric flux compactifications over Q have some arithmetic to them, and in particular, they're modular. And so we still don't entirely understand what's going on physically, but to my mind, this F-theory construction is a sign that there is some physics underlying these point counts. And so I'm cautiously optimistic that this is an early sign of a deep relationship between string theory and arithmetic geometry. And to end on a high note, I want to emphasize what the sort of dream of this would be going forward. And the dream is that we would love to get a physical interpretation of the Fourier coefficients themselves. We don't know where they come from physically, but since the Fourier coefficients control everything, it would be great if we could know where they come from physically. And there are sort of conjectures in math about what the AP should mean. And if we could compute them physically, really know what they mean, maybe physics can provide some insight into arithmetic geometry. So that was what I had to say. Thank you all for listening. I appreciate it.
All right. Thank you, Richard, for the very nice talk. Let's all thank Richard with our clap emoji. Our first question is from Yunan.
Hi. So it's pretty nice that you can construct like a supersymmetric vector systematically like this. So, but I just wonder, like physically, whether after a modular stabilization, you are naturally located at the supersymmetric vector, like a specific value of this modular field or not. Like
So for these continuous families, we had to restrict ourselves to rational phi. There's a whole one parameter family, and we had to make a choice of restricting ourselves to rational phi more or less by hand. So that's one of the things we would like to understand, is whether something special happens for these rational guys. For isolated supersymmetric flux vacua, they are associated to a point in complex structure moduli space, and that point either does or does not admit a model over Q. But in many cases, supersymmetric flux compactifications come with rank 2 attractors, and rank 2 attractors are always defined over some number field. So in that case, you inherit the some arithmetic from the arithmetic of the rank 2 attractor.
So it's like your conjecture that this thing should be rational, and it's like, and also it's like for a particular model, how do we expect the total number of the supersymmetric flux vacua is gonna grow, or what was the approximation on the total number of flux vacua?
Well, so the first thing I want to say is we certainly don't conjecture that all flux vacua are defined over Q, because we know they're not. If I take my example of one parameter, my one parameter example, and take phi equals, like, I don't know, pi, then you definitely can never get a rational model for that point in moduli space. The claim is, if I'm sitting at a flux compactification where I can define it over Q, then it's modular. And then as for how the number of fluxes is expected to grow with Hodge number, I don't actually know. I think that the answer is, in general, we expect there not to be any, because we have to solve over constrained equations, and that in fixed examples you can look and maybe you can find them. It's closely analogous to the question of how many rank 2 attractors do you expect there to be, and most Calabi-Yau threefolds don't have any rank 2 attractors. Like, for instance, the quintic has no honest rank 2 attractors or supersymmetric flux compactifications.
Okay. Thanks.
Mm-hmm.
Okay, we have time for one more question from Severin.
Hi, yeah, thanks a lot for the talk. This was very interesting. Is there anything similar for twofold for K3s? I don't know if you mentioned any.
Mm-hmm. So I didn't talk about it, but there is a result for K3s. So in K3 surfaces, the analogous result is that singular K3s, K3s with maximal Picard rank, are modular and associated to rank 3 modular forms. So that's the analog of the attractor story and not the flux story. But that is the analog of K3 surfaces. There is, mathematicians are still interested in understanding modularity of K3s of rank not 20. That's still an open question, but for singular K3s, it's a theorem. It's not even a conjecture.
Mm-hmm. But any relation between, similar to what you had for threefolds, between fluxes and modularity?
So flux compactifications on K3 are kind of, well, okay. So one thing to emphasize is that the flux story is strongly dependent on dimension. And the reason why is, well, I mean, there's many reasons why, but the flux modularity story in particular is strongly dependent on dimension. And it's because of this FH in 2, 1 plus 1, 2. So the Hodge type of the 2-dimensional subspace determines the weight of the modular form you're going to get. And so to get a weight 2 modular form, you need 1, 0 plus 0, 1, 2, 1 plus 1, 2, 3, 2 plus 2, 3, 1 plus n, 0 plus n plus its complex conjugate. You can't get two-dimensional subspaces of that form in K3 surfaces, so there can't be something like flux modularity. You can't get a weight 2 eigenform. You can look for other modular forms, and the kind you naturally get are weight 3, but there's nothing like a weight 2 story.
Okay, yeah, okay, thanks a lot.
Okay, time for one more question from Fabian.
Thank you. I just wanted to ask if so in your construction with the blow up, essentially, you included y goes to square root of a times y. So if I was looking at the field extension of Q by root A, these two manifolds would be the same?
Yes. So this particular choice of coordinate rescaling, it's pretty famous in the study of arithmetic geometry. It's called a twist, and the idea is, yes, it is. If we're working over Q adjoin A, so okay, the first thing is, if A is a perfect square, then of course this is a Q isomorphism. For A not a perfect square, then this is an isomorphism in Q adjoin A.
Yes.
Of course, it's also a C isomorphism, but it's not a Q isomorphism, so the modular forms will change.
Exactly, but if I was working over the field extension by root A, then they wouldn't change. So
they would be completely isomorphic, yes.
Good, thank you.
Okay, great. So thanks again, Richard, for the very nice talk, and thanks to both of our speakers for very nice talks today.